I thought that was you.
Someone arrived here on a Grand Cherokee vehicle. They parked out front and they left their vehicle, left the door open. But we have closed the door, so you're not worried about it. It's okay, but I hope you have a key because it's probably locked. Today's topic is climate change. We have talked about this before with other programs, and we will do it again. And that you'll see on the back of the program, the one that's scheduled for next fall, is another program dealing with the subject of climate change. The Rothermel Foundation is not dedicated to discussing climate change. We're dedicated to discussing ideas that you will find interesting and that may be challenging your thinking a bit, and you'd like to have more information. And we would like to say that we are having some success in providing that for you. The subject of climate change is the one in which North Carolina is a big state. We have a lot of discussion on all levels in our communities, some of which are informed lectures and informed points of view, and some people who are operating on a, let's say, almost on an empty tank when it comes to talking about the subject, which is so important to us. Our job is not to take a position. Our job is to keep you informed. That's what the Rothermel Foundation is all about. I would tell you that the Rothermel Foundation came into existence as a result of a legacy left by a member of the Presbyterian Church, Rothermel. He left a nice gift in his will, and that has led to people very interested in these kinds of discussions, of being sure that the public understands the interconnectedness between everything that you do, and it's not compartmentalized like science and religion, and that they do interact with each other. And we are looking at the same discussions that go on that are important for us to make good decisions. Mr. Rothermel was an engineer by profession. He came to live in New Bern at the time of his retirement, and before he left New Bern by way of the cemetery, he before he left us again, he left a legacy behind which you and I are enjoying today, and we hope that you will see it that way. Our purpose is to explore truth. To explore truth emanating from available knowledge, rooted in good science, free of baseless opinion, to assist our audiences to make informed decisions regarding this matter that is capable of touching every aspect of our being, from our quality of life ultimately to our survival. And that's not to put too much pressure on our speaker for today, but it is an important topic, and one which our board has felt strongly about. And we think your presence here today indicates that you feel strongly about it too, and we hope you'll find this informative and pushing ahead. I will tell you that there will be a break at the end of our speaker's presentation. We will meet for refreshments, as I said earlier, in the session house, which is just to the right as you go out the back of the sanctuary. Then we'll reconvene here for questions, and you have academic cards. And those questions we'll have them arranged in groups so that we can use your time efficiently and our speakers' response time efficiently to try to deal with topics that you have on your mind. And there will certainly, there's always a good bit of overlap. Now, let me say a word about our speakers for today. Dr. Bruce Wielicki comes to us from NASA. You have information in your program about him, and I'm not going to try to repeat all of that, except to say that he's a senior earth scientist at NASA. He has labored in this media for a long time. He holds the PhD degree in physical oceanography from the Scripps Institute of Oceanography. He has published over 100 journal papers with over 5,000 journal citations. Now what that means, I point that out to you among all the other stuff we put in here, is that if other people are referencing your work, means you're doing something worthwhile. Otherwise, they ignore you. And so just the fact that you've never written up 100 papers doesn't mean necessarily there were 100 good papers.
My father means
But having come from the science background myself, I can tell you that other people are citing your work. It means they're finding something worthwhile in what you're doing, and they want you to keep doing it. He served as a project scientist on NASA field experiments, co-investigator of 4 NASA space missions, including studying clouds, aerosols, and radiation. He's been principal investigator of NASA's Cirrus instrument, which examines clouds and his Earth's radiant energy system, and currently serves as the science team leader for NASA's CLARIO, which is climate absolute radiance and reflectivity observatory mission. You see why they do acronyms. Nobody can understand the name. Anyway, I'll point out these parts of what we have printed for you in your program. There's more there that you might want to know. To let you know that we've got a real professional here to talk to us about a topic that's very important to all of us. And we will all be anxious to hear what he has to say and to be able to ask him some questions about things that are still needing addressing with further reaction. I guess without anything more, let me introduce to you Dr. Bruce Wielicki.
We'll see how I do under pressure here. So I always like to start by reminding people that we scientists are nerds, introverts. We don't actually like being out in front of 250 people. We really want to be back in our office with the computer, typing our little equations and doing our little analysis. However, for climate change, a lot of us have found that we're working in an area, field that's complex. There's a lot to it. And it almost becomes a responsibility for us to get out of the lab and really talk to people about what we know. And we're always very hesitant to do that because the first time you do it, you're trying to communicate to people not in the science field, which we're used to. You've never given public lectures, you're very nervous about whether anyone will understand anything you say. So about the mid-90s, I started trying to do that. My first one, only 4 people showed up. Imagine that was a little embarrassing. But it was the first public lecture I put together, and it taught me a lot about how to think about my field in a different way. So since then, I've done about 50 public climate lectures. So my blood pressure is down a little lower than it used to be, living in front of a group like you. But I'm really great to see you here, to see this big a turnout. And I really hope I can help you understand more about climate change, how to separate the wheat from the chaff, and really start to understand where to go look for information on climate change. So without that, let's go further. So NASA, where I'm from, has been involved in looking at the Earth for a long time. This is the best we had back in the 1960s. This is sort of a global view from satellites. Africa's over here, the US is over here. It looks kind of kludgy because it was. It had to be kind of cobbled together from different weather systems. It didn't really look very coherent. This is the way we see Earth today from space. We have a lot of different space observations of literally dozens of different climate parameters. This is a current view from a Lotus instrument on a Terra spacecraft up in orbit now. We pretty much look at everything from vegetation, ice sheets, oceans, atmosphere, chemistry, a wide range of things. In addition to all of NOAA's and other global data on weather, what the oceans are doing, and what the ice sheets are doing as well. All that's pulled together in understanding climate. So I need to start by helping you understand what climate is, because there's still a lot of confusion with this. Technically, climate is the long-term average of weather. It is related to weather, but it's a long-term average of it. And in weather, we know theoretically there is a 14-day prediction limit. 1,000, a million years from now, you will never be able to predict weather beyond 14 days. It's physically impossible. We've got the equations to prove it. We've done the experiments to prove it. So don't ever expect good weather prediction beyond 14 days. That's dynamic. You're trying to predict where things are moving in exactly when and where they'll move, or a storm or a hurricane's going to go. That's driven by dynamics. And you only get about 1 degree accurate data for weather, whereas climate, which is the long-term average of weather, has no known predictability limit. For example, if I want to know what the decadal average temperature is going to be as I change things like carbon dioxide in the atmosphere, the only limit on that right now is natural variability itself, which I'll talk about. And the longer the time average you give me, the more natural variability is peaked down to lower and lower levels. So it's a very different problem than weather is. We tend to ask the question, if I can't predict weather beyond 5 days, how could I ever predict climate and energy in the future? And the answer is, it's like asking a physicist, we talked about this last night at dinner, if I had a single particle and had to predict where it's going to go, it's a tough job. If I only have to predict what the average of all molecules in this room are going to do, that's a lot easier job. That's climate. Climate is the average of a lot of systems working together. It's an energy problem, whereas weather is a dynamics problem, very nonlinear. Energy is a very linear problem. I'll give you another example. You're going to boil a pot of water on your stove. You know how much heat your burner puts out. You know how much water's in the pot. You know the mass of that water, its heat capacity. You can calculate how long it takes to fully boil hot water pretty accurately. That's climate. Weather would be instead asking the question, what second of time is the first bubble going to form on the bottom of that pot, and where's it going to go up from? That's a very different question. It's a really hard to predict. But climate is instead the average of what the energy is doing. Very predictable problem. So weather accuracy, the other thing, 1 degree is enough, but climate accuracy is more like 1/10 of a degree. So it's about a factor of 10 tougher measurement. And so this is some of the challenges we have in our observations, is to put together observations accurately enough over decades to understand what we know and don't know. So climate in that sense is much more than weather. It's ocean circulation, it's sea level, it's salinity, it's biosphere, it's greenhouse gas chemistry, where it's carbon dioxide going, it's ice sheets, it's snow and sea ice. So it's a lot bigger problem than weather is. So the first thing to understand about the difference between weather and climate is variability. What's natural variability? What you'll hear a lot about climate change is we're not causing warming of the planet. This is just natural variability of the Earth system. So let's talk about that a little bit. What is the natural variability of the Earth system? So I'm from Virginia, up near Yorktown, and here's an example of Virginia daily mean temperatures in March 2010. They ranged from 61.5 degrees down to 35.5 degrees within that single month. So we're talking a 30-degree range in temperature. That's weather at short time periods. Now you could also ask, what are monthly mean temperatures in Virginia over 30 years from 1971 to 2000? Here's that range. It's about 9 to 10 degrees Fahrenheit instead of 30. A lot less variability because now I'm averaging over a month. I'm not asking just what is instantaneous daily average temperature. Then finally, what about global annual? This means average all the data over the whole globe for a year. What's that range? That's very small. We're talking a little over 1 degree. And actually, a lot of that change was actually slow warming of the planet, not natural variability. So what you'll find is that the bigger the time scale I go to, the bigger the spatial scale I go to, the more you're going to find that natural variability is going to reduce. It's going to drop. And you're going to see much more clear signals. This is why you in your backyard aren't seeing as clear climate signals as we as scientists looking at the entire globe can see. Or we're looking at the entire US. Or we're looking at the entire tropics. So you have to realize when we're a scientist studying climate, that's the kind of discrimination we're looking for, to see these signals and where we're going. So here's another example in Virginia, was March 2012, was a really warm, anomalous month. Matter of fact, across most of the US, this is the warmest month that had ever occurred in terms of climate anomalies in the last 130 years of records. And here's this, again, for March 30 years, the variability was here, and this year was way up here. Matter of fact, this was so warm, it was about where you might expect Virginia to be if we go on our business as usual in 2100. It was an example of how you are stepping out of natural variability into the beyond, even for a single month's worth of temperature. And that same month of March 2012, here's Virginia, pretty warm, right? This scale is in degrees centigrade, so you need to double those numbers to get Fahrenheit, basically. So 2 degrees centigrade is about 4 degrees Fahrenheit. Virginia was about 5 degrees centigrade or 10 degrees Fahrenheit warmer than normal. And you can see that there were still regions that were cooler than normal in that month. Some were cooler in blue, some were warmer in red. You see kind of a mixture, you see more red than blue, but that's natural variability from spot to spot for where weather systems are moving in a single month, 1 month. So let me now back off from 1 month and ask what's natural variability look like in another month. Some of you may remember our last winter was pretty chilly. So here's January 2016 over the entire globe. And here we are in the southeast, in North Carolina and Virginia, and actually it's white, which means it actually was a perfectly normal winter. We thought it was cold, but it's only because we've been warmer than we used to be. It felt cold to us. It actually is normal. So the rest of the world now, you'll notice, was mostly very warm. Especially the Arctic was phenomenally warm. It's up here in the black, up around 11 degrees C, which is like 21 degrees Fahrenheit warmer than normal. And the Arctic is warming the fastest, by the way, of the entire planet. It's warming 2 to 3 times faster. We'll talk a little bit more later about why. So now let's look at a full year. So now let's look at the last year, 2015. This is now for the entire globe of the last year, and you'll notice, except for a little pocket in the North Atlantic, and we actually predict this in our climate models, that should stay a little cooler, which is related to ocean circulation as we melt ice off Greenland and sea ice. That's now showing you warmth almost everywhere, and a little bit of cooling in the Antarctic. Now you start to see eastern U.S. is about half to 1 degree C warmer, or 1 to 2 degrees Fahrenheit warmer than normal. In fact, the entire world, the global average, was about 1.5 degrees Fahrenheit warmer than it would have been before climate change. Now you can ask, what happens if I do a 10-year average? 2005 to 2015 over the whole globe, and now you'll see it's even more uniform, right? As I go back to the lower averages, you see more and more variability, right? But as I go to longer time periods, you see all this smooth out. The world gets much more coherent. This is the boiling pot of water on the stove. It's not the bubble. And you're getting away from weather. You're getting into the climate change that we as scientists are talking about. Now the world is a much more coherent place, all moving in the same direction at the same time. But you'll notice there is this dramatic increase up in the Arctic. It's warming a lot faster than the rest of the world. And that's because as we warm the Arctic, we warm sea ice, and we take something that was ice reflective, that reflected sunlight back to space, and we turn it into water, which is dark and absorbs energy. So as you warm the Arctic and get rid of some of that sea ice, you amplify the carbon dioxide warming by additional sunlight. The same happens with snow in the northern hemisphere on land. We are getting less and less snow over time in the high latitudes because we're warming the planet. That reduces the amount of sunlight scattered to space and warms us further. That's why all these high latitudes are warming much faster than the rest of the globe. And the other point here is that, in general, you notice the oceans are warming a little slower than the land. That's because they have a big heat capacity. The land changes its temperature very rapidly day to night. The ocean does not. If you go out in the ocean, you know its surface temperature doesn't change very much day to night. It moves very slowly. And that's just the thermal heat capacity of the ocean. So the rules of natural variability are, it's everywhere, it occurs on all time and space scales of weather and climate, but it's largest at the smallest time and space scales. Use New Bern here. New Bern temperature at 7 p.m. on a given day. That's where you get the most variability. It's smallest at the largest time and space scales, say a global average over an entire decade. And dynamics, movement of air, is what gives you the noise at the shortest time and space scales. Think cold fronts, thunderstorms, hurricanes. Whereas energetics dominates the largest time scales, seasons, ice ages. Remember, your weatherman doesn't know how to predict very accurately the weather for 2 weeks from now, but you yourself know how to predict the July average temperature difference from the January average temperature. That's called a season. That's the difference in heating of the sun, summer versus winter. It's very predictable. That's climate. Weather is just moving weather systems in and out. That's basically noise to a climate scientist. So that energy system I've been talking about is shown here. Sunlight coming in, 342 watt per meter squared. Think of this as 3,500 watt light bulbs over every square meter, every 3 by 3 foot section. That comes into the Earth. About half of it gets absorbed by the surface. Clouds reflect a bunch of it back to space. About 30% of it gets scattered back to space, half absorbed at the surface, and about 20% absorbed in the atmosphere, mostly by water vapor. And then we have to get rid of all that heat, or the Earth is heating up. So the way we do that is we emit in the thermal infrared. Think sitting by a fireplace when you're camping, you can feel this heat radiating off that fire. That's infrared heat. You can't see it with your eyes, but it's there. It's radiation just like sunlight, but it's at wavelengths your eyes don't see. That's how we cool back to space. It turns out that if the Earth had no atmosphere, and we had our current absorption of solar radiation, the temperature of the Earth would be way below zero, 30 degrees below freezing. Because, as a simple ball, that's all the sunlight we're getting. The reason we're warmer than that is greenhouse gases, like carbon dioxide, like water vapor. That's what keeps our planet warmer. If we didn't have an atmosphere in those gases, this would be a frozen rock you'd be living on. We would not be here. So, those greenhouse gases are what cause our climate that we have, because what they do is they absorb this infrared radiation trying to come out to space, and then some of it gets sent back down, and some of it goes out to space. What the Earth is trying to send out is almost 400 watts from the surface, but only about 225 is getting through the greenhouse layer. Think of this like putting blankets on yourself at night when you sleep. The more blankets you put on, the harder you're going to get, even though the room temperature is the same. It's the same with our climate system. Think of CO2 as additional blankets. The more CO2 we put out in the atmosphere, the more blankets we add on top of us in terms of keeping the system under the CO2 warm. So that's the way that works. So what is the human influence on climate? What does it look like? So let's look at a longer time scale now. Here's 1,000 years ago, 1000 AD to 2000 AD. Here's carbon dioxide trends. How do we know carbon dioxide over 1,000 years? We're going around to measure that. Well, we get this out of the ice sheets. Turns out as the snow falls on Greenland and Antarctica and eventually packs the ice, little air bubbles are stored in the ice. We can do cores back to actually 800,000 years ago. And we can take the air samples out at a given level. We can map it back in time, and we can know what the carbon dioxide was because the air is actually trapped in the ice sheet. Same with methane. We get methane and other greenhouse gas the same way. And sulfates, these are the aerosols we put out our tailpipes or we put out of coal-burning power plants. And we can also see sulfate aerosols in those ice sheets as well. And so you'll see all these have spectacularly risen just as the Industrial Revolution started and we started burning a lot of coal and oil and natural gas. So we are the source of this CO2 and the methane and the sulfate change. Then if you looked at global temperature trends and how do we get those over 1,000 years, we can get them through the ice sheets because it turns out there's oxygen isotopes that are a function of temperature where the ice sheets are. That's one way. But we can also get them from tree rings. We can also get them from boreholes. Holes, you know, if you go in a cave, the temperature is more like the annual average. Or the deeper you go into the earth, the more it averages back in time. And we can get them from coral reefs. And if you put all those together, this is the reconstruction you get of the temperature over the last 1,000 years. And it was very slowly, about 1/10 of a degree centigrade over 1,000 years, going colder. What's that? Well, that was us moving toward the next ice age. The rhythm of ice ages and interglacials is really caused by our orbit around the sun. We don't have a circular orbit around the sun. Sometimes we're further, sometimes we're closer. The tilt of our planet varies over time. It wobbles. And so that eccentricity of the orbit, when it occurs during the year, and the tilt, all cause these 100,000-year variations. It turns out in all those variations, the average sunlight that hits the Earth never changes at all. All that happens is it slightly changes which part of the year hits what part of the Earth. That's enough change in energy to drive the ice ages. That shows you how sensitive the Earth's climate system is. So we were going to reach the next ice age in about 50,000 years. So it's a long time off. We didn't have to worry about it anytime soon. However, you'll notice when the Industrial Revolution took off, what happened? All of a sudden, temperatures started going up dramatically. And if I extrapolate to 2100, here's the range of temperatures we think we're going to be looking at. So this is where we were, and we took over the planet right here, and this is where we're going. Okay? We have been running the Earth for hundreds of years. We're going to be doing it forever. So we better figure out what we're doing. So I'm going to talk about what some of the potential impacts are. And you'll notice these are pretty significant uncertainties. By 2100, you might warm 1.5 degrees C or 3 degrees Fahrenheit, or you might warm 6 degrees C or 12 degrees Fahrenheit. That's still within the 90% confidence bounds of our uncertainty about how much we're going to warm. And it's primarily what's called climate sensitivity uncertainty, which is how much of the clouds going to change as we warm the planet. It's actually the research problem I've worked on most of my career. We still are struggling to answer it. Here's another way to look at this in terms of understanding what's going on. Here's looking back over the last 10,000 years of history in the paleo data. And this is now temperature from the ice cores. And you can see it's varied a few tenths of a degree. This was the warmest part of the last interglacial. And then going back down. And now we want to put that into the scope of where we're going in the future. It's on the same scale. You just have to go way up here to talk about what we're talking about. The geologists now are ready to start calling this the Anthropocene. This is a new geologic era. It is the era when man, anthro, is controlling the world and climate. So the geologists themselves are only arguing about what year should we start the Anthropocene. They're not arguing about whether we are in the Anthropocene. So that just gives you a sense of how big the scope of this change is. And here's putting that now on a scale. Remember I said you could go in the ice cores back to 800,000 years. Here's the ice ages coming and going. This is carbon dioxide in the atmosphere. There is a little bit of variation with the ice ages themselves and how much the ocean can hold. Here's where we were in 2008. So we were already out of any natural system mode. We actually passed that well ago. Here's where we think we'll be in 2100 if we start cutting our emissions. Here's where we think we'll be in 2100 if we go business as usual as we currently are going. So we will be way up here. So what does that mean to be way up there? Another way to look at this is, take the last 400,000 years of the ice sheets. Here's the sea level records. You can see sea level varies by, and this is in meters. So this 120 meters is 360 feet of sea level. When we're in a glacial, we are put 350 feet of sea level up on glaciers, up on the land. And you can see there are times sea level was above what it is today. Like 120,000 years ago, we were at the current temperature we're at today, slightly higher than what we were 100, 200 years ago before the Industrial Revolution. That level of sea level rise, turns out, maps to about 12 to 18 feet higher than it is today. And I'll talk about sea level rise a little later, about what it means for us and where it might go in the future. The other thing we have is we know what surface albedo is from the ice sheets increasing albedo back. That's part of what causes the ice sheets. And then greenhouse gases, which also affect it. We know how much energy that is putting in and out of the system. And then we use our climate models to try to predict in these green curves what temperature the Earth should have under those conditions, and our observations from the ice sheets to try to predict what really was going on. And you can see they actually agree pretty well. This is part of what gives climate scientists confidence that while our models still have uncertainty, they're in the right ballpark from past 800,000 years of data of ice sheets coming and going, and CO2 coming and going for how much it should respond. So how does the Earth respond? We are currently forcing it by adding carbon dioxide to the system. The Earth then changes, warms, it can make more moisture. As you warm the air, it's going to hold more moisture. More moisture in the air becomes an energy source for storms, convective storms, hurricanes. Water vapor itself is greenhouse gas, so as I warm the air, I add more greenhouse water vapor to it, so I warm it even more. So it turns out water vapor is a positive feedback. It about doubles the amount of warming we're going to get, as if relative to the Earth having no water vapor. And then you're finally going to get feedbacks. If I start changing temperature and water vapor, the clouds might change. They might change how much sunlight they reflect back to space. They might change how much greenhouse gas they trap. And so they literally could start changing in both greenhouse energetics and reflectance how much they change the planet. So that's kind of one of the wild cards. That's the climate sensitivity uncertainty I talked about before. And our climate models that try to do this coupled Earth system, they start with the water and energy cycle I talked about. They add atmosphere and ocean dynamics. They model the entire atmosphere of the entire ocean. They add atmospheric chemistry, things like aerosols, things like biomass burning we do of forests, of agriculture, the methane we put in the atmosphere, and then the carbon cycle. They have to keep track of how much carbon dioxide that we put in the atmosphere. About half of it over 100 years will actually get taken up by the ocean. You may have heard the ocean acidity is increasing. That's from the ocean sucking up about half of the CO2 we put in the atmosphere. But the rest of the CO2 we put in the atmosphere is going to stay there for thousands of years, because as the ocean gets more acidic, it can't take up more CO2. So it will get to a certain adaptation level, but then to actually allow it to take more, and this has been shown in the past paleo data, the time scale for the ocean to fully take CO2 out is about 50,000 years. And that's because it has to wait for the mountains to weather, more basic chemistry to come down the rivers and literally replace the ocean and make the ocean more basic so it can suck up more CO2 to get its acidity back up. That's literally the long time scale way that the climate system will eventually get rid of the CO2 we put in there. It's just going to take it 50,000 years to do it. So you should realize that what we are in for, let me contrast that with aerosols. You're familiar with air pollution, really hazy days. You've probably seen the pictures of China, Beijing, with people with masks. The horrible aerosols problem they have is basically their coal-burning power plants and their cars. They don't have the air pollution standards that we do. They're racing toward them rapidly because their people are unhealthy in that environment. It turns out if we stop producing aerosols, in 2 weeks, they will all have rained out in rainstorms, and there will be no more aerosols. CO2 is going to stay there for 50,000 years. So we're talking two very different problems with air pollution and global warming or climate change. The carbon dioxide we put in the system, half of it will go out in the short term in the ocean, but half of it will be there for many thousands of years. So that's the commitment. So not only a few generations later than us are going to have to deal with this, literally hundreds of generations are going to have to deal with this. So how do we understand how much we've changed the climate versus natural variability has changed the climate? You'll hear a lot of people talk about this is not climate change, it's just natural variability. So let's look at that. Our climate models include everything from the effect of solar variability. We've measured the sun at high accuracy for over 30 or 40 years. We have volcanic eruptions, really big eruptions like Lagoon, El Chichon, and Tubo can actually drop the temperature of the Earth a few tenths of a degree centigrade or almost half a degree Fahrenheit for a few years. Human forcings of carbon dioxide, methane, aerosols, ozone, and land change. Now, this particular first chart in blue just shows us natural forcing only. So don't use any of the human forcings, just use the natural forcings, put it in a climate model, and blue is what our climate models predict, and the little scatter is natural variability of the system itself. That's just the noise you're going to get from El Nino, from La Nina, from Pacific Decadal Oscillation, kind of nonlinear wiggles, the kind of natural variability I talked about in the past in those earlier charts. The black line are the actual observations of the Earth as a planet from 1900 to 2000. And what you can see is right about here, 60 or 70, we started getting outside the realm of where natural variability could explain our variability. So what do we get if we put human forcings in? This is the exact same plot, but now my climate models are adding the carbon dioxide we put in the atmosphere, the methane, the aerosols, the ozone, and land change. Because when we deforest, we change the albedo of the land, we change the reflected back to space, for example. The main effect is CO2. Aerosols are second, and then the others are kind of behind that. But now you see a much better agreement between what our models predict should happen physically and what we see in the real world. You can also look at this by continent. You get a little more noise at continental level. So now these ranges here are, red again is with human forcings, blue is without. And here's North America from 1900 to 2100. You can see we kind of left natural variability at the continent scale about 1980 to 1990, depending on which continent you were at. But even they at the continent scale are all now out of natural variability. They're all beyond the ability to explain that from natural variability. So, not coincidentally, this is about when the IPCC started doing the reports, 1990. This was when the science community was serious enough about climate change and understanding it well enough that they were getting very concerned about where the world was going and how we were going to deal with it. So what's the more recent record look like? Some of you may have heard about a hiatus or slowdown in warming. Some people have even seen things on the media or the internet where they'll say, it's not warming, it's cooling. Well, how could that be? And they're actually showing you the correct data. So let me explain how that can be. Here's the actual climate record. The annual values are the dots. The blue line is a 12-month running mean of all the global temperatures. All right? It goes all the way up to recent, right up to 2016 up here. The red line is a 132-month or an 11-year running mean. So you just keep moving a 10-year average all along the data. That smooths out a lot of the internal noise of the system. So like El Niños, which are 5-year time scale, they get averaged out when you do a 10-year mean. So now the red line is closer to what the mean climate is doing. And now I'm going to blow up what they call the hiatus. I'll show you that here. This is just the very end of the same plot. So look in 1998. This was the El Niño of the century. El Niño tends to warm the Earth's temperature. La Niña tends to cool it a little bit. So when you see a plot that says we were doing global cooling, they will start in 1998 with their plot at the peak of the natural variability event. And then they'll do it maybe down to about here, which is about 15 years. And they'll say, aha, we're cooling. Or you could pick another period over here, we're cooling. So if somebody shows you a 10 to 20 year record temperature, they're cherry picking a little piece of data and they're using natural variability to confuse you. Don't ever believe a 10 or 20 year climate record. That is not what the climate system is doing. And I hope with the explanation of natural variability, you now understand why there is noise in the system at those time scales that the longer you go, the more and more that averages away and the more and more that goes away. So the bigger the time scale and the bigger the space scale, you will then start to see the real thing, which again, if you go back here, now you'll notice the last couple of years we had jumped up dramatically. Right? So suddenly what looked like a dip is just natural variability over a few years. Once you look at the big picture long term, you see a different story. So what are the global temperature predictions? So this is out of one of the IPCC reports. They're all currently pretty similar to this actually. It hasn't changed that much. This is 0 to 6 degrees centigrade. So think of this as 0 to 12 degrees Fahrenheit. And this is from 2000 to 2100. These are all different climate models. And this inner blue is uncertainty due to how much we're going to do in future emissions. Are we going to go in a lower path or a higher path? And then there's another blue around that, which is uncertainty in climate sensitivity that I talked about. So for example, let me give you an example of how that works. Say as we warm the planet, that low clouds, and they mostly reflect sunlight back, but since they're low, they're close to the ground, they're about the same temperature as the surface, and so they don't have much greenhouse effect. They don't have much warming effect. They just cool by reflecting back to space, kind of like snow would do on the ground. Well, it turns out if you just slightly drop low cloud cover as you warm the planet, you will increase the amount of solar energy absorbed to the surface. That extra energy will amplify the amount of warming you get from carbon dioxide. If the opposite happens, if instead the clouds increase as we warm the planet, you'll get more reflection back in space, which will offset some of the carbon dioxide warming and give you a lower climate sensitivity. So basically the clouds are the wild card in this business. And right now we still have a factor of 4 uncertainty in climate sensitivity at 90% confidence. Is the biggest scientific thing we're trying to deal with as we have academy studies and others. And that's what's causing a lot of this big range in our ability to predict. We wish we could tell you that it's 3 degrees plus or minus a little bit, but that's not what we have. So the IPCC report, not only does it tell you what we have as our best prediction, it tries to give you a sense of what are the uncertainty bars on top of that. And we're going to have to deal with society at both the low level of this and the high level. And I've worked with economists on this to try to understand the economic impacts. And what they will tell you is the following. There's 2,000-page economics reports from the IPCC that come with the science reports. That the economic impacts of future climate change are roughly the square of the amount of warming we get. So if we get this warming that's 4 times bigger, we will have roughly 16 times more economic impacts. So there's a really strong leveraging. So why isn't it linear? You might think it would be linear in warming. The reason is that all of our infrastructure is built to handle current natural variability. We built it based on experience over 100 years. We designed our infrastructure for that. Once climate goes out of that natural variability, and we're now going there now, then we start to overwhelm our infrastructure. We start to have sea level rise that overwhelms in Tampa their sewer system because the water's coming up too high and they can't get water out. You have to start redoing sewer systems. So a lot of things start to add costs non-linearly, and the economists have studied this for about 20 years, and that's their best understanding of what our future economic impacts are. And if you want to understand how big those are, if we're up in this range, we're talking about 5% of global gross domestic product in damages every year. The recent financial crisis we had was half to 1%. So it's literally 5 to 10 times bigger than that. On the other hand, if we're down here at the low end, maybe we're in the 1% level, so maybe we're about half to 1%, more like the recent financial crisis. But that's going to go on for decades. Keep going on every year, and it's going to build because the planet's going to keep warming. One of the things about warming is that we have only seen half the warming we've already committed to. The reason for that is the oceans are a huge thermal heat sink, and it takes them a long time to warm up and get into equilibrium. The oceans are not in equilibrium with our current CO2 level. The land is. The land responds much more quickly, but most of the world is ocean. So those oceans staying cooler yet because they haven't warmed up enough are holding back the amount of temperature change we've seen. So we have only seen half the warming that we've already, in that sense, committed to. And as we add CO2 over these next few decades more into the atmosphere, we're going to be committing to yet higher levels. So that's kind of the stakes of what we're doing as a society. So what does it look like as more of a regional map in 2100? And this shows you what happens depending on whether or not we get serious about reducing emissions. Here's a global map late in this century. If we get serious about global emissions, how much warming occurs in degrees centigrade. And again, double those for degrees Fahrenheit. Here's what happens if we don't get serious about it. Now you can see that especially in the Arctic, I mean, you're off the chart off to the right. You're literally talking about 25-degree warming in terms of degrees Fahrenheit in the Arctic. There, you have no sea level, I mean, you have no sea ice in summer at all. You also start to melt more rapidly, Greenland and Antarctica. So we're still arguing a lot about that ladder, about what happens with sea level rise. If you want another way to visualize what the 10-degree Fahrenheit warming at the end of the century might look like, you can look at current climate zones and ask where they would move to. So, for example, Washington, D.C.'s climate will become like Tallahassee, Florida, basically, at the end of the century. And you can imagine that Tallahassee, Florida is going to be in a totally different zone it's never seen. You had 10 degrees, and the other thing to remember, if you know what dew point is, dew point will go up the same level as temperature, and dew point is what makes you uncomfortable outside. If dew point's in the 60s, you're comfortable. If the dew point's in the 70s, you're muggy and you're miserable. The highest dew points we get here in this last muggy summer were 78 degrees. In that scenario, they would get up to 88. You cannot cool your body at 88-degree dew point. You will literally run from an air-conditioned building to an air-conditioned car and spend no time outside in the summer in the southeast if we get that one. It's not that you can't live here, it's that you can't live here without air conditioning. And places like the Middle East, it's seriously questionable when you can live there. So what are the hazards in terms of sea level rise? I live in Yorktown, the Hampton Roads area. We have a big military base there in Norfolk, one of the biggest in the world. It's sitting right at sea level. So the military is very aware of this risk. How much sea level rise are we talking about? In our current climate models, and sea level rise is still very uncertain for two reasons. One, for how much we warm the planet is still uncertain, as I talked about. The second reason it's uncertain is the dynamics of the ice sheets and how fast they melt is still an early area of research. We know it takes, from the paleo data, really long times to grow ice sheets, but to understand how fast we are forcing the climate system, the same amount of energetic forcing we are doing with CO2 in 100 years takes the Earth's interglacial system in our orbit around the sun 100,000 years to do. We are forcing the system 1,000 times faster than it has ever been forced before. So we don't know the answer from past data. We don't know how fast the ice sheets can accelerate their loss. We do know what level they got to in the past, so we can show you that, and I will. But our current estimate is that our best guess by 2100, and this will be early sea level rise as we warm the planet, is anywhere from half a meter, 1.5 feet, to 1 meter, 3 feet. And depending on whether we do a lot of CO2 emissions up here, or less CO2 emissions, we get more serious here, you can see we can reduce maybe a factor of 2 that range of sea level rise we might get. So there are things we can do to help. But what does the paleontological data of past history tell us about the amount of sea level eventually we would get to? And this, for me, is perhaps the most concerning plot. This comes out of a book by a geologist called Archer. You can go look this up if you want. Here's the last glacial maximum 20,000 years ago. Sea level was about 350 feet below where it is now. Here's where we are today. And here is 120,000 years ago when the Earth was at today's temperature. And if I go across that axis, you can't read the value very well, but I can tell you what it is. The seas were 12 to 18 feet higher then. Okay, and that's where, at today's temperature, that's how much ice that Greenland and Antarctica want to lose to get into equilibrium. Now, they haven't lost it yet because the ice sheets can't respond instantly. It does take time. We don't know how long. If you now look at the IPCC forecast I just talked about for 2100, and you try to understand what the implication of ice loss is, it's those red lines. You go up to, there are past times when 3 million years ago we were here, and 40 million years ago we were much even warmer than we would be in 2100. And at that point, there was literally almost no ice on the planet. 220 feet is melting all the ice sheets. So in the long run, it may take hundreds to thousands of years for the ice sheets to melt, but it won't take more than a few thousand. Then you get to 150 feet of sea level rise. That's the kind of climate change you are committing to in the really long term. Not 2100, don't mistake that. I do not mean that in the next few decades you're going to see spectacular sea level rise. But I mean as a society for many, many generations, and remember that time scale of CO2 in the atmosphere is thousands of years. It is at the time scale where the ice sheets will have time to acclimate. They will have time to change. So basically over hundreds of thousands of years, that is where sea level wants to go if we do business as usual and keep emitting CO2 as we grow society through this century. So what does that mean for locally? So let me show you what it looks like. Here's Pamlico Sound, current coast. This is from NOAA. And they have these really nice maps. You can play with them yourself online. Here is 3 feet of sea level rise. This is that upper level that I showed you in the IPCC expectation. And all of these areas in blue are now inundated. Okay? Those are all underwater. They used to be above water. And here's 10 feet. Remember I talked about that 12 to 18 feet that current temperature wants to head toward. There's what you get with 10 feet. One thing you do notice is there was a bigger shift with 3 feet than we got with 10 feet. Which means it's pretty flat over a lot of this area. Then, let's go and zoom into New Bern. So there's you. There's where you'd like to be right now, and where you'd like to stay to be, especially if you're living on the water. By the way, my house in Yorktown is in the mountains of Yorktown. We don't realize we have mountains, we do. They're 50 feet high. I am one of the highest places in Yorktown. I built that house in 1987. I was a climate scientist back then. I did not want to go near the water. I didn't know what the answer was, but I knew it might not be good. So here we are, New Bern, current coast. Okay, are you ready for it? Here comes 3 feet. There's 3 feet. And there's 10 feet. So it's not that New Bern's going to totally disappear. There's still some of it there. But also, as I said, if you now ask me, will New Bern be here in hundreds of years? The answer may be no. The same for Hampton Roads. If we're going to let the ice sheets equilibrate and keep putting CO2 in the atmosphere, they are eventually going to get up to many dozens of feet. But it may take many hundreds of years. It may take 300 or 400 years before you see 20, 30, 40 feet of sea level rise. But all these coastal areas are not going to survive 20, 30, 40 feet of sea level rise. So this is what's at stake in the really long term. When you see IPCC reports, they're only talking about 2100, but you need to get in the back of your head. That's not the worst case scenario. This goes on for thousands of years that we have started. And the only way out of that is to suck CO2 out of the atmosphere. And I can tell you, it's an incredibly stable gas. It takes a lot of energy. You can suck CO2 out of the atmosphere. It's just incredibly expensive. We are doing experiments to try to learn how to do that. I think future generations, 50 years from now, will be spending a lot of time trying to learn how to do that because they're going to want to get it back out. Every CO2 molecule you and I put in there, they're going to have to pay to get back out. So what are the 3 laws of climate change? I would say accuracy in the data and the science, which I've tried to give you a sense of. Accuracy in public information, this is a really serious thing out there. The internet's a wonderful thing, I love it, I'm on it all the time. But it's also full of chaos. It's also full of agendas, it's full of basic advertisements, very slick-looking science-like websites that are total garbage. They are trying to sell you a political message, they're funded by fossil fuel companies, they're funded by political agendas. Don't go there. Accuracy in policy making, we're really struggling with that, as you can imagine. So where do you go for accurate information? What is the IPCC I kept talking about today? This is called the Intergovernmental Panel on Climate Change, started in 1990. It's sort of organized by the UN. It's all the governments in the world, and we literally gather climate scientists from the entire planet. Thousands of us work together on writing a 1,000-page report every 5 or 6 years. What have we learned in peer-reviewed journals in the last 5 or 6 years about climate change? What is our knowledge? What's our uncertainties? What are we trying to solve? And that is all then boiled down into that. And then there's a bunch of economists that work with us to try to understand future potential economic impacts and even the costs of mitigating climate change. So all that's in the IPCC. That's your best single resource. Major scientific organizations, the AAAS, the American Geophysical Union, the American Meteorological Society, the U.S. Global Change Research Program. These are all thousands and thousands and thousands of scientists. Don't believe me. I'm trying to show you mainly what the IPCC shows. That's the gospel, the best wisdom the world can give you right now. Don't trust any individual scientist. I will guarantee you nobody is without an agenda, me or anybody else in this room. So the advantage of those big scientific organizations around the world is they average over all that noise, just like climate over weather noise. And every organization, major scientific organization in the world, in every country, all basically supports the IPCC assessment as the basic best knowledge. So try not to listen to the latest paper or the latest result or the latest individual on the web. So the American Association for the Advancement of Science, AAAS, has millions of scientists. They've been there since 1884. American Geophysical Union is about 50,000 in 137 countries. They've been there since 1919. American Meteorological Society, 14,000. These are the kinds of organizations you can trust to have some sense of what's going on and not to be an agenda-based. So what can you do about it? That's a pretty depressing story. And I don't want you to leave or have a heart attack right now or anything else here. There is good news, so let's talk about it. What can you do? One, you can try to buy more fuel-efficient cars. You can get back to 2 more fuel-efficient cars today. The technology is already out there. You just have to decide to buy them. You can make your house much more efficient. Go to the Energy Star website and Google energy yardstick. That'll let you put in your zip code for climate, the size of your house, the number of people living in it, and how much electricity, natural gas, or oil you use to heat and cool your home. It will give you a rating from 0 to 10 and let you know how good you are and how much you can improve your house. And I can tell you, I did this myself as a climate scientist in 2006. Living in my own custom home I built in 1987, built very energy efficient. And I was pretty proud, and I thought, I got up about a 5 and I can improve it better. Well, I did that test and I found out I was a 0.7. Now, as a scientist, I knew I screwed up the data. So I put the data in, and it still came back 0.7. So then I sat at the computer for an hour, shocked. I was literally, you don't talk shock and awe. I didn't know what, I was embarrassed. So I thought, all right, I got to find out about this. So fortunately, one thing good about the internet, You can find all sorts of information about anything. So I started digging into, why is my house so inefficient? What's going on? Well, it turns out it's lots of little things. There is no one thing. It's sealing air leaks in your house where pipes and electrical wires go up through your walls. It's sealing leaks in your ducts. Most of us throw 20 or 30% of air conditioning and heating out through duct leaks. It's putting cellular lines on windows because they add nice little air pockets and they add R3 to the R2 of your window and they make your windows lose 2.5 times less heat than they normally do. There are lots of little things. No one thing that really costs all that much. You can take your most attic insulations are at 19. You can go to R60 and almost totally eliminate any heat loss through your attic. It's not hard to do. You blow it in, it's pretty cheap. And you will get paid back dramatically. I'll give you an example in just a minute, so let's go on from there. Bottom line is most in the US could cut their emissions by 50%, whether it's cars or homes, and still save money, not cost yourself a dime. You will pay yourself back, and I'll give you an example in a minute of how much. Where do we need to go to? The answer is we need to get to at least 80% reduction in emissions. We're not talking 20, we're not talking 30. If we want to control climate change, we need to get to 80. You have to eliminate 80% of your emissions. The other thing you can do is support the development of renewable energy and wind. I'll talk about that. It's a lot more optimistic story than people realize. You can support more rigorous climate science. I will tell you right now, I love to use this analogy, we don't have a climate observing system. We have a weather observing system, we have research observations. It's like me being nearsighted and wearing somebody else's glasses. I can see, but not very well. And that's what we're doing as climate science right now. We have not, as a world, put together a climate observing system. I'm arguing with the science community to try to get us to do it. I think eventually it will happen, but it hasn't happened yet. And the most important thing is think long-term about what you're doing now, short-term. Most of us have genes that were designed to avoid lions, tigers, bears, and storms. Really short-term threats. This is a long-term threat. Society is not well suited to deal with it. We have to think this way, though, because the stakes are incredible for future generations, not only our own generation. So here's what I did at home after my 2006 shock. I then started doing those little things I talked about. And I added insulation in the attic, I sealed my ducts, I did air leak sealing, I had cellular blinds, I had a programmable thermostat, I put in LED lights, I reduced vampire electricity. Oh my gosh, you just get a little thing called a kilowatt and plug your things into it and find out how many things you think are turned off that are sucking 50 watts of power. 365 days a year, 24 hours a day. Unbelievable amounts of energy just thrown away. Useless. I didn't make any windows changes, heating changes, or air conditioning changes. None of the big buck things. Didn't change them at all. Here's what I now use. I use 40% of the electrical energy, and as of 2012, I was down to 50% of gas. I'm now down to 40% of gas use. So I've eliminated 60% of my carbon emissions. It cost me $9,000 to do, and this is the curve of savings over time. I was at that point saving $1,800 a year. I'm now saving $2,000 a year. So basically, it was about 2013, 6 years after I started, that I paid myself back. So for the last 3 years, I've been paying myself $2,000 tax-free every year, and it will keep going on for as long as I have that house. So you have a gold mine sitting in your home that not only can you help climate change, but you can save yourself all sorts of money. Second, when will renewable energy drop below fossil fuel costs? Everybody thinks, oh my God, it's going to take forever for us to get solar and wind where they're cheap enough that we can afford them. No, in fact, they're already there. Solar and wind power in the US are currently about 4 to 6 cents a kilowatt hour. That's the total cost of implementing them. And residential electricity is usually twice that at 11 cents a kilowatt. The newest solar projects in really good solar areas like the Middle East or China are 2.5 cents a kilowatt hour. They're way below what we're paying for electricity. Natural gas, if you put in a new natural gas plant, it's about on average 7 cents a kilowatt hour for the best ones. So we're already at the point where solar and wind installations are as cheap or cheaper than natural gas, which is cheaper than the other things you can put up. There's another thing called the learning curve. The learning curve applies to any technology, not just solar. It says, as I double the total cumulative production of any item, whether it's a car or a solar panel or anything else, the cost will drop by X% every time I double cumulative production. And there's two things going on. One is technology advance, because you're pushing technology for things you're building. And the more you build of them, the harder you push the technology. And two is mass production is cheaper. The more I'm making of something, the cheaper I can make it. Turns out, you can look at the 30 or 40 years of solar, and that learning curve is 20%. Every time we double the amount of solar, we drop the price by 20%. So what's happened? Turned out, solar has already dropped by a factor of 200 from the 1970s in cost. So now, we're at currently 1% of global electricity is from solar. By the time we get to 2%, solar power is going to cost 80% of what it does today. At 4%, it's going to be 64, 8%, 50. You can see the story here. By the time we got a third of our power from solar, it's going to be 1/3 of the current cost. And it's already as cheaper than current energy sources. We're headed to a world where we can get energy 10 times cheaper than we currently get it from fossil fuels. Is that a scary story to you? I don't think so. So it's another one of those gold mines for us to find. Wind power, what's that doing? About 5% of U.S. electricity in 2015, and the current, this is levelized cost of energy, the sort of life cycle cost of energy, is about 6 cents a kilowatt hour, back about where natural gas is. And the learning rate is 5 to 10%. Same story is going to happen. Not quite as dramatic, so maybe only a factor of 2 increase. Offshore wind, by the way, I will caveat, is still more expensive than onshore wind, so it will take probably another extra 10 years to develop and get the cost down for offshore. We haven't done much offshore wind is the problem. It's very early in the learning curve, and it's more complicated than onshore wind. But it will get there as well. So how about the intermittency of wind and solar? They're not always there. How are we going to deal with that? How much land in the U.S. would we need to do solar and wind as our full energy sources? Well, Germany, I can give you a data point. They've been working on this much harder than we have. They're already up to 30% of their electricity from renewable power, and they have had no grid stability issues. We're way behind that, by the way. So we have ways to go. Wind tends to be high when solar is low. So actually, there's kind of a complementary nature of those two. So you really always want to have both of them, not just one. So you'd really want a combination of wind and solar across, and then transmitting across the country. The Midwest, by the way, from Texas to North Dakota, has by far the best wind power resources, other than offshore off the East Coast. And then the Southwest, California to Texas, has the best solar power resources. Offshore wind, and you'd want to put them 20 miles offshore so you can't even see them from the coast. They're literally so small that they're about that big if you look at them at that distance, is where you'd want them. And off the East Coast, we have so much offshore wind capability, we could power the entire U.S. just with offshore wind. But it's not yet cheap enough. So you're not seeing a dramatic amount of it yet. You're still seeing all these arguments about, we shouldn't put windmills out there because they're going to ruin the view. Well, you just put them out there 20 miles and you won't ruin the view, you won't even see them. So, 0.6% of the U.S. land is enough solar to power the entire U.S. You don't need a lot. Battery technology to solve the intermittency, that's coming along very rapidly. It's currently $190 a kilowatt hour. That's Tesla and LG are both there, 2 different companies. At $130 a kilowatt hour, lithium-ion batteries are so cost-effective that they can solve the solar and wind intermittency, meaning the added cost of the battery still keeps electricity below current rates. When are we going to get there? Well, it turns out at the rate they're building them right now, and again, the same learning rate is there for batteries. Learning is 20% per doubling of production, just like solar is. It's been doing that for decades. It turns out in 2 to 4 years, Tesla and GM will be there, and basically we'll already be building electric cars and batteries that could be used as storage for solar and thermal power for the electric system, cheap enough that you can now afford it. And the learning rate, as we start to expand them, is going to keep going up. So those electric cars are going to get cheaper than any other car you can buy to own in terms of total ownership. So again, we're not only going to be as cheap as today's energy in cars, we're going to be cheaper than today's energies in cars. So it's a great story, actually, but we all have to wake up and move in that direction. If we just do what we've been doing, we're going to get a bad outcome from what I talked about before. So the bottom line, climate change is very serious. We need to do something about it now. We're currently committed to an unsustainable future. Climate change economic impacts in 2050 to 2100 on our current path are 1 to 5% of global GDP per year, and 1 to 5 times bigger than the economic crisis in 2008 that will continue for decades. Time to change from hunter-gatherer. If you think about the way we do fossil fuels, it's hunter-gatherer. We hunter, and we find something, and we pull it out, right? It's not farming. Solar and wind farm energy from resources that are already there. It's time to move out of hunter-gatherer mode into farming mode. We're going to farm energy the way we farm agriculture. It's the same basic idea. All the key technologies for solar and wind power are already cost competitive, and they're going to get better. Battery storage is literally within a few years of being cost competitive, and it's going to go reduced by further factors of 4 to 8 as the growth increases with electric cars and power storage. So we have all the technology tools we need to economically succeed in this transition. And remember, we've transitioned energy before. We used to use wood originally, right? Then it went to coal, then it went to oil. This is not the first energy transition society has made. This is the first one we're going to have to make on purpose. So there's where I'll finish. That's my Tesla. After all my energy savings on getting a Prius instead of a minivan, which cut our gas costs to and saving $2,000 a year on our house, I finally got up to $47,000 of energy savings. That's over what I invested in what I had bought. So this Tesla would still cost you like $58,000 to buy credit, and I don't normally buy cars over $30,000. So this was a big step for us, but this car, relative to an equivalent, say, Mercedes luxury car, which it's like, will save you $30,000 in fuel over its life. So that 58 suddenly becomes a $28,000 car. If you think long term, you make a very different economic decision than if you think short term. And this battery technology is improving so rapidly that this kind of car, Tesla's coming out with a Model 3 in a couple of years, and there's a GM Bolt that's coming out this year. They're going to cost about $30,000. And you add the fuel savings, you can literally almost get the thing for free. And they drive a whole lot better than a gas car. No transmission, no oil changes, much better handling, much better acceleration. Once I've driven a car like this, literally after 5 minutes, I said, I don't think I would want a gas car again. And that's had nothing to do with energy saving, it's got nothing to do with carbon emissions, it's just a better technology. So I think the bottom line is our future can be healthier, less aerosols and crap in the air, cleaner, cheaper, and more fun. And I'll stop. If you want to see the Tesla, you park out on the road.
Okay, we have actually quite a lot of questions. We're still getting questions. Unlike me, who was very afraid to pose a question to a NASA scientist, apparently you all are unafraid. Okay, we may not get to all of them, depending on the length of the answers, and there was not a lot of repetition. So we'll see. We'll do the best we can. So you did talk a bit about the force changes versus natural variability. So we have some questions on force changes. One of those is, what percentage of carbon released into the atmosphere is man-made versus natural? Volcanoes, fires.
So of the increase I showed you, that's all man. We can actually track what the sources of carbon are by different oxygen isotopes, different isotopes of chemicals. The actual fluxes, there's a lot of fluxes from the ocean, from the land, from everything, but that all balances out as part of the carbon cycle itself. In terms of actually increasing, you can show that all that increase in carbon dioxide is man-made sources. Some of it's burning of forests, some of it is burning agriculture, some of it's burning most of it's burning fossil fuels, basically.
So we have another question. This is on deforestation. So how has deforestation affected climate? And also, especially effects and progress in third world.
That's a good one. So we struggled with that for a while in climate science. We finally, through a lot of satellite data and estimates over the globe of deforestation, settled that it's about somewhere in the range of 15% of our carbon emissions are burning of forests. We are doing deforestation faster than we're doing reforestation. There are parts of the globe that are actually bringing trees back where they had been wiped out, but there's more than that where it's being cleared, basically in the tropics for agriculture typically.
This has to do with methane. So what effect does methane have on warming of our atmosphere along with CO2?
So methane is a significant greenhouse gas. It's like CO2. It's not as big as CO2. The other thing about methane is it doesn't have as long a lifetime. So it takes a few decades, but CO2, methane, which is CH4, it's basically carbon and hydrogen, will literally convert itself to CO2. So what happened is over a few decades, and it's a good thing because methane is a lot stronger greenhouse gas than CO2 is. But it eventually converts itself to CO2 and then it will stick around a lot longer. So methane is a significant part of the story, but we haven't seen anywhere near as dramatic increases in methane as we have in CO2.
Okay, while we're on the subject of CO2, if government regulations force U.S. companies to conserve CO2 at high cost, will they be forced to move to countries without regulation, i.e. what can be done to make it a global equal playing field?
That's a very important one, and I think it's very true that what we need are global solutions, not just national solutions. But what you will see at the very end of my talk was the technologies to do this at not higher cost are already there. As a matter of fact, the technologies around the world are there so that if you become the country that drives those costs down the fastest, you're going to be most successful in international trade in selling those technologies. So right now, the job market in wind and solar power is increasing dramatically. And so the plot of how solar is being installed in the world is just skyrocketing. And I think we want to be part of that market. And so I would not look at it as a disadvantage. I would actually look at it as a technological advantage for us to be more involved.
Okay, we have a couple of questions that are more communication related. These I didn't need too much help in interpreting, so I'm more comfortable here. So this one is, I work with a faith-based nonprofit educating on climate change as a faith issue. What other ways can we share the science in a way to get past the noise of current culture? I'll just go ahead and read the second one, which is, what is the best response to our elected officials who are proud of being climate change deniers?
That's a juicy one, because I even talked to some of those people myself. There are congressmen in my area who are climate change deniers. I think the strongest message to give them is that we as a society need to act on the best cumulative wisdom of the science community. It's what I talked about in those scientific societies. Those are the big picture understanding of the whole science community, not one individual scientist, not one company, not one congressman. They have to get past their own ego and their own local concerns and think more globally and think more long-term. And that's where I would point them to. Look at climate statements in all the major scientific organizations. Look at climate statements in things like the IPCC. That is the best current scientific wisdom you will get. And every 5 or 6 years, you'll get a newest, updated version of it.
Okay, these next few questions have to do with effects on our oceans and water. So raising sea levels have focused on impacts on humans, but the impacts on estuarine systems and fish resources are an even greater threat. So please comment on that. Will the melting Arctic ice decrease the salinity of the ocean off Labrador and possibly shift the Gulf Stream? And lastly, assuming further melting of the polar ice cap and glaciers, when the latent heat of ice melting is used up, will the ocean increase in temperature, accelerating?
So that's a juicy set. So in terms of the estuaries, they will be affected. I actually have a brother who works in wildlife. He runs the South Carolina Waterfowl Association, so he's very involved in estuaries and water birds. He says the experience they've seen in areas like Louisiana where things have been inundated is that actually estuaries can change relatively rapidly, perhaps more rapidly than we thought. So as flooding occurs, they will shift. They won't immediately shift to the full system that's been there for hundreds of thousands of years. They'll have some ability to recover, but it may take many decades to recover, if not 100 years. But of course, if you keep inundating, which is the kind of sea level we're going to get, you're going to keep outrunning the last estuary with the new estuary. So it will be an ongoing problem, and certainly marine biologists are studying it. It's not really my area of expertise, so I can't give you too much more detail on that. As far as Arctic sea ice melting, the sea ice itself kind of comes and goes. Its actual volume is not that large. What's a bigger issue is the amount of ice that's coming off the Greenland and Antarctica ice sheet. And those and their interaction with the ocean is really the sensitive area. For example, in the Antarctic, turns out there's something called the West Antarctic ice sheet, which they think was caused the 12 to 18 foot of sea level rise we got 120,000 years ago, because it's anchored on ocean bottom, hundreds of meters below the ocean. It's literally ice all the way down to the bottom. But once you melt it free, then the ocean gets deeper behind it. And so literally you unanchor the ice sheet and it starts flowing much faster than it does today. So most of the ice sheet uncertainties about how fast they can respond are actually wrapped up in the ice sheet equivalent of weather, its dynamics. You don't actually get rid of ice sheets by just melting them at the top. When you melt them at the top, instead what happens is that water flows down through the glacier through cracks and fissures. If you've ever been on one, they're full of cracks and fissures. Lubricates the bottom of the glacier, and then if there's a slope for it to run down, like a mountain glacier, that's how they disappear. They literally run downhill, and at lower altitude it's even warmer, so it accelerates their warming, and it accelerates how fast they go away. So that's the process we're trying to understand with ice sheets. Did I miss one there?
Salinity.
Salinity. So salinity is not as big a deal. It will be in some of the surface waters near the glaciers. The bigger deal with salinity will be, not so much salinity, is ocean acidity. As it sucks up carbon dioxide, the ocean gets more acidic. A lot of the plant life in the ocean at the base of the food cycle depends on ocean acidity for making its shells, for example, calcium carbonate shells. The white cliffs of Dover in England are all old foraminiferous shells that went down to the bottom of the ocean. So that and coral reefs and other parts of the ocean ecosystem, there is concern about how much ocean acidity it can stand before you start seeing rapid changes. But from what I've heard of fishery stocks, the bigger issue we have, at least today, is actually overfishing. But when you put that overfishing together with changes in ocean ecology, then you sort of have double stress on the ocean system.
Simon Winchester, author and geologist, estimates that mankind can survive 1,000 to 10,000 years. Are you this optimistic?
Boy, that's a tough one. I would not bet on humanity going away. Humanity will still be here. The question is how many and how successfully and how stable. I don't think this is something where entire human civilization will go away. But it is a destabilizing force. You have to realize that. So we're in church here. So one of the things about stewardship is not only to be stewards to us locally, who are the best off in the world, but to be stewards to the poor of the world. Well, the poor of the world face the biggest impacts of climate change. They live in the tropics, where it's already the hottest and the moistest and the hardest to live. They're very poor. They don't have air conditioning. So as it gets hotter, they're going to have a tough time on it. And they're often living close to sea level. Think Bangladesh. Really poor people, very poor water sources, and those people are going to be stressed a heck of a lot more than we are. So in my mind, stewardship, in the big picture of society, you're going to destabilize a lot of marginal societies as you do climate change. This is why the military considers climate change the biggest security threat the U.S. has in this century. The military got climate change a decade ago. They've already been writing reports on it. So they don't agree with the climate deniers at all. They will tell you this is a big deal and we need to work on it now.
Okay, this is probably a question that you're used to getting. You say climate accuracy is 0.1%. How do you calculate a global average surface temperature when at any time Earth temperature ranges from Arctic to equatorial? Explain where your data comes from.
Good question. So ultimately we want a climate observing system where all our data is traceable to international standards at like 100th of a degree Kelvin, and we know every data set and how accurate it is. We're not there yet. But what we do have is many data systems. So for temperature, let's take temperature. We have a surface air data set, all the NOAA surface air stations around, right? And the other countries have similar ones. We have radius-on balloons that take temperature from the surface all the way to the top. They go up every day, every 12 hours, all around the world. That's an independent set of data. We have ocean ships that all take ocean water in as a coolant and measure the temperature of that water constantly as they travel across the ocean in all those shipping lanes. We have all that data. We have ocean buoys that are anchored in place for decades, and they take surface and deeper ocean water. They literally drop chains of measurements thousands of feet into the ocean. One recent buoy they put in place is literally anchored 5 miles down, and it takes temperature and salinity that entire way. We have another set of temperature measurements called Argo flows. They are literally battery-operated floats. They're about 3 feet high and maybe about a foot in diameter. They live at about 2,000 meters or 6,000 feet deep in the ocean, more than a mile. And then every 10 days, they change their buoyancy and they float up to the top, taking temperature and salinity profile all the way up. They telemeter to a satellite data, and then they sink back down to 6,000 feet again. And they do this every 10 days for 5 years until the batteries die. And by that time, we replace them with a new one. And we have a network of those every 200 miles over the entire ocean system. We have that data. So we have satellites measuring temperature in both the microwave and the infrared. We have temperature measurements from what's called GPS that lets you navigate. It turns out you can use the refraction of that signal as it goes through the atmosphere. As I look from one satellite here through the very edge of the atmosphere, the limb of it, to the GPS satellite, and the way that refracts is a function of the temperature profile in the atmosphere. And that's really accurate and really traceable to international standards. We have that. So we have literally about 7 or 8 independent temperature data sets, no one of which could tell you the whole story, but they all give the same story. They all say we're going through roughly the same warming. You can argue at the small level, maybe you can argue about the accuracy of that record at about a third of the level of natural variability I showed you. That's kind of the noise between our different measurement systems, but they all show the same warming. And they all show the Arctic warming faster. And they all show the Antarctic not warming quite as fast. So that's how, as scientists, we currently build up confidence by using non-ideal data. We do it by many independent sources. That's how we get confidence. Very good question, by the way.
This one actually goes back in time on the data. So do any of the models go back further than 800,000 years? If so, what do they show? There's a second question, which I think is a little tongue-in-cheek, but if you know anything about our state politics, it says North Carolina has legislated sea level rise. So we'll be fine, right?
Let me do the first one first. Yes, we've done climate models to even try to predict something called the PETM, P-E-T-M. It was a huge thermal maximum where the Earth, over millions of years, had above normal volcanic emissions. And when you have that, you actually put more CO2 in the atmosphere over millions of years. It took a long time, but it did eventually get CO2 levels up to where we are likely to take it if we keep it business as usual for about another 150 to 200 years. So while the Earth system took probably 10 or 20 million years to do it, we could do it in 200. And that experiment has been run on climate models. And it does also show dramatically higher temperatures as the paleontological data does. It shows we could literally get to 15 to 20 degree Fahrenheit global warming. No ice sheets. It's all melted. Sea level is 230 feet higher than today. And that's a world we could put ourselves in if we don't decide not to. Now the second, in terms of sea level rise, and whether we can legislate it, I would suggest that the real Earth system doesn't care much about our legislation. I think what you're seeing in that legislation is what I would call the current economic infrastructure afraid of change. They're very concerned about their own economic value, which they should be. And that's true of the fossil fuel industry. It's true of coastal development, coastal real estate, for example, whether you build it or whether you sell it. And so those people have a lot of economics at stake. And they will work very hard to not think very hard about climate change or to go to a denier site online and convince themselves that it's okay. We know we're all very good at rationalizing, by the way. It's only a matter of how well and when we do it. So this is a requirement of society to reach beyond individual interest groups to a broader solution. But we should recognize the fact that those special interests will be hiring a lot of lobbyists in a lot of states and in the federal government. I've gone for NASA training on how Congress works in the DC, and I can tell you they have documented that there's something like 100 lobbyists for every congressman there. 100 lobbyists. Now some of that, be careful, some of that is actually useful information helping Congress understand what's at stake. However, the fact that we let them give them money, give them trips, influence them in ways that are financial. California, by the way, as a state, from what I hear, does not allow that. That's illegal. We should be making it legal. I don't think there's anything wrong with giving information, but there's something very wrong with using money to provide it. And so I think in that sense, lobbying could be improved in our country, but you should realize that there are a whole lot of special interests, and they're working very hard.
Okay, well, here is a different kind of special interest in our group here today. We have a ceramic artist among us, and he or she asks, I use a 220-volt electric kiln in fire to 2,280 degrees Fahrenheit over an 8 to 15-hour firing time frame. Can you talk about the effects of ceramic kilns and what impact they have on our environment natural versus the natural gas kilns?
That's a good one. What you could do is you could try to figure out I give you an example for emissions of natural gas. What they call a CCF, 100 cubic feet of natural gas, and it's 12 pounds of carbon dioxide. The electricity emission of carbon dioxide depends on your state. And it depends on how much nuclear you have, how much solar and wind you have, how much coal you have, and how much natural gas you have. Natural gas emits about half of a coal-burning power plant for the same electricity. Obviously, nuclear doesn't emit. So an average over the whole country is about 1 pound of CO2 per kilowatt hour. So for every 11 cents of electricity you burn, it's about a pound of carbon dioxide. The average person in the U.S. emits 50,000 pounds of carbon dioxide a year. And there's a lot of us. And so we are the highest emitters per person in the world. We in Australia get that honor. If you go to China, they emit about 1/8 what we do per person. So don't worry about China being this problem. Yes, they have 8 times more people, which is why they have as much emissions as us now. But all the agreements are for them to keep their emissions per person well below ours and even well below where we want to get ours. So everybody's trying to march to a world where we can all have a standard of living that's comparable, and our carbon emissions per person are comparable in a fair sense. So that's where we're trying to get the world to go to.
Okay, we just have a few more questions. I'll save the best for last, which had to do with your Tesla.
That was
Any
a
other?
long time.
Yeah. Let's see, we'll start with this one. Please discuss extreme weather associated with sea level and temperature changes.
Good question. So, extreme weather, as we warm the Earth's climate, one of the biggest things we do is we increase water vapor in the atmosphere. And that's called the Clausius-Clapeyron relationship. And basically, relative humidity will stay roughly constant in the atmosphere. It doesn't matter where you are, winter, summer, polar, tropics, huge ranges of temperature, but relative humidity is always about the same. So what happens with temperature is as I warm the air, it can hold more water vapor. Every 10 degrees centigrade or 20 degrees Fahrenheit I warm the air, it can hold twice as much water vapor. And that just keeps going on for as much as you want to warm the air. Well, now think about what storms get their energy from. It's water vapor being condensed into liquid. That is the storm, that is the energy source for thunderstorms, that's the energy source for hurricanes. So as you warm the Earth's planet by 10 degrees Fahrenheit, you can imagine you're going to increase the amount of moisture by 50%, say, and you're going to then give those storms 50% more energy to work off of. So it is predicted to increase the severity of storms. We expect precipitation to be more extreme when it happens. On the other hand, the total amount of precipitation, we don't expect to change that much, primarily because that's limited by how much sunlight we get at the ground evaporating water. That's the source of water in the atmosphere. And that's limited pretty much by do we change sunlight or not. So pretty much we think that the mean precipitation over the whole globe is going to change very modestly, but it can get more extreme. So you may have longer droughts and more extreme floods. The other thing you'll change in precipitation is the Arctic. Right now it's mostly frozen. Permafrost is going to go away as you warm the planet. It's not going to be permafrost anymore. It's going to be frozen in the winter and melted in the summer. There's going to be more rainfall up there because you're going to warm that area 3 times faster than we're warming the rest of the planet. And so its moisture source is going to double or triple. And so it's going to have a lot more water vapor to turn into rain than it does now. So you will get more rain and precipitation at the high northern latitudes of the Earth. So extremes can get more extreme. One of the ways climate scientists say it is the climate models seem to predict that as you warm the system, the wet will get wetter and the dry will get drier. And that's true both in time and in space. And we do think that the having circulation, this is where air rises in the tropics, like the deep tropical convection zone. You see these huge bands of thunderstorms across the whole Earth. That then drops down in the subtropics, like where the deserts are. That's why they're deserts, because the air is moving down and it's not allowed to move up and produce rain. That is expanding as we warm the climate system. So the desert areas will expand some as we warm the climate system. So there will be more dry area in that scenario we expect than what we currently have. So that's kind of the extreme story.
We had a late-breaking follow-up question to that. Do aircraft vapor trails have any measurable effect?
That's very good, because the expert on that is right down the hall from me at Langley. He has actually satellite data to count contrails from aircraft all around the globe and actually monitor how they're changing seasonally, what they do. It's an incredible story. But he's also then calculated how much, and these are thin clouds. They don't reflect a lot of sunlight, but they're up at very cool levels, so they do have a greenhouse effect. So he's calculated both from his observations, and the answer is it's there, but it's pretty small. It's one of the smallest contributors to climate change. It's not zero, but it's probably one of the last things you're going to worry about.
Okay, just before we get to your Tesla, the next group of questions had to do with lithium batteries. Let's see, a pre-question was, is nuclear power a thing of the past? Is lithium the future? What about lithium batteries? What is their life? Are they rechargeable, disposable, recyclable? How does this affect the environment in terms of their disposal?
Good set of questions. So having a Tesla, which has a lithium battery, I did a lot of research before I bought that car on exactly these questions. And what I can tell you is that lithium, we have enough lithium easily accessible on the planet to roughly build about 1 billion cars. So we can build a lot of them. We don't have an infinite amount of lithium, but we actually have quite a bit. However, for storing power from solar and wind to be used with our electrical system, I think lithium will actually be the short-term answer because it's advancing most rapidly of the battery technologies. But I think things that are called flow batteries, where you just literally take metals of different density, layer them in a big container, and it becomes this huge, big, bulky liquid battery, are going to ultimately be the cheapest batteries to do for power system storage. And I think that's what they're going to go to, but that may still be 5 or 10 years down the road. The transition, cost-wise, will be lithium. But long-term, I think they'll shift to a different battery technology. And you should realize there's many battery technology options out there. Sodium, lithium, aluminum-ion batteries. So there's literally 20 different battery chemistry technologies that are being advanced at the same time. The likelihood we won't succeed in batteries is essentially zero. Whether it will exactly be lithium, lithium's getting all the attention right now because it's being advanced so rapidly, because it's been in development for so long, that learning curve I talked about has gotten lithium now down to the point where Tesla's building a gigafactory, where they're going to, in 2 years, be producing from one factory in Nevada as much lithium-ion batteries as the entire world produced in 2013. One factory. And they're not going to be the only one. There's going to be a gigafactory in Europe. There's going to be a gigafactory in China. There's going to be a gigafactory in Korea. LG, the company LG, is racing in battery development, as is Panasonic, as is one of the other Japanese companies as well. So there's many different battery technologies being developed. The Tesla uses they're a little bigger than a AA cell. There's about 7,000 of them in the car. It's literally just a flat panel at the bottom of the car, weighs about 1,000 pounds. And right now, they're about 190 degrees a kilowatt hour, which is the amount of energy. And they expect with the gigafactory running in 3 or 4 years, they will be at 130 kilowatt hour. At that point, electric cars will be less expensive to own than any gas car. So literally, we are at the very front end of a huge transition. So I think there are some dinosaurs on the planet that you are still walk around right now. Gas cars are a dinosaur, oil is a dinosaur, natural gas is a dinosaur, and coal is a dinosaur. They're all going away, but it's still going to be a transition. It's not going to happen in an instant. The good news is all those other technologies are going to be cheaper, they're going to be cleaner, and they're going to help us with climate change. And from driving a Tesla, I can tell you it's a hell of a lot more fun than a gas car to drive. Oh, disposability. Turns out lithium is incredibly recyclable. So that Tesla battery, when it is done, will be recycled for its lithium content. We'll be able to get all that lithium back. The lithium density in that battery is literally more than 1,000 times what it is in the normal mine you're going to have. So it's going to be the cheapest lithium source you're going to be able to find as you renew it. So basically all lithium will be recycled in batteries. It's not right now because we have these little things that people are disposing of. But in terms of mass use of lithium in power company batteries, which are going to be big, they can get 100 kilowatt hours in roughly a refrigerator-sized battery. Those are the kind of batteries that the power companies are going to use. And eventually people with solar on their homes, if they really want to go off the grid, can put those batteries in their garage or outside their house.
Okay, so you drove your Tesla here. Bill mentioned earlier that Rothermel departed New Bern by way of the cemetery. God willing, you will be departing New Bern by way of your Tesla. So one of our questions here is, my friends who live outside of Washington, D.C. want to drive their Tesla S to New Bern to visit. Will they encounter any recharging problems? And then another question, what is the cost of electricity to run your Tesla?
Good question. So I didn't need to recharge at all to come here with my Tesla. It'll do about 240 miles of range. And I have the smallest Tesla battery. The biggest one's about 310 miles of range. Tesla has what they call superchargers every 130 miles along all the interstates. And those will recharge your car in 30 to 40 minutes. So the way you drive a Tesla long distance is you go from supercharger to supercharger. And they put them at malls and places with coffee shops and restaurants. So you'll drive for a few hours. My wife and I have taken our Tesla from Virginia to Tennessee and back in the winter for Christmas to see my family. We've taken it a couple times to the mountains of South and North Carolina. We've obviously taken it here. And the way you drive it is you drive for 2 or 3 hours, and then you stop at a supercharger, you go get a cup of coffee or whatever for a half hour. We typically tapas eat when we do this. Instead of big meals, you'll have a little hors d'oeuvre and a cup of coffee, and then you'll drive for 2 or 3 hours, get out, use the restroom, stop, have another hors d'oeuvre and a cup of coffee. And that's the way we drive. And it's very relaxing. It's actually a very nice way to drive. Now, the future of that, so your friends in D.C. will have no trouble getting here in a Tesla. The network of Tesla superchargers is currently about 80% complete around the country. They're putting them in at the rate where probably in about 9 months it will be totally complete. You'll be able to drive anywhere in the U.S. with the Tesla superchargers. When I got here to charge, the local area inn had a little Tesla charger at the B&B, so I just charged for free overnight at the B&B. It's very cheap to charge. You asked about the cost. So many power companies will give you cheaper power at night than during the day because nobody's using it at night. So I, in Virginia, can get power for 5 cents a kilowatt hour at night. And that's when I have my Tesla set to charge it. So here's the way you use a Tesla. Drive home, you put a 240 volt 50 amp circuit in the wall. Cost me $200 to have an electrician do it next to my electrical box. And then you plug your Tesla charging unit with about an 18-foot cord into that. It just sits on the garage wall. When you drive your car home at night, you just take the cord and plug it into the Tesla. It doesn't matter whether it's raining or dry or anything. It can sense all the electricity flow and you can't get shocked by it, even if it's raining. It takes 10 seconds to plug in, you walk in your house, you leave it. It's set at 1 a.m. to start charging. My wife drives 100 miles typically a day. She has a long commute back and forth to Virginia Beach. It'll charge that much in about 3.5 hours. So I get this 1 to 5 a.m. window of 5 cents a kilowatt hour. And then all the supercharging on the Tesla network is free. Tesla pays for it. It's really built into the price of your car. So that ends up costing me 1.5 cents per mile for fuel. If you took a current Mercedes-Benz with the same power that car has, that car is 0 to 60 in 5 seconds, and I have the slowest Tesla, you would need a 400 horsepower gas car to be equivalent to that car in capability, and it would get about 20 miles per gallon. So in terms of equivalent gas cost, I'm paying the same as if you were able to get 35 cents a gallon gas. That's my cost. I'm about 6 times cheaper than gas for an equivalent capability car. So you will save a lot of money driving a car like that. And then in 2 years, Tesla will have a Model 3. That would cost about $35,000. Over the life of my current Tesla, relative to that nice, fancy Mercedes, I will save $30,000 in fuel. So my $70,000 car drops to 40. If you wait for the $35,000 Tesla, you can drop it down to 5 relative to a high-performance car. Or if you get a lower performance Tesla, maybe you're comparing it to a 30-mile-per-gallon car. Maybe you only save $20,000. But the bottom line is going to be when you do the full cost of owning a car, an electric car, here's some other things you probably haven't thought about. An electric car has no oil. It has no engine. It has an electric motor with about 8 parts. Your normal engine in your car is 1,000 parts. Your transmission, your 6-speed automatic transmission is 1,000 parts. My Tesla has a 1-speed gearbox. There's no shifting. It has like 6 gears that just change the RPM from the electric motor to the wheels. That's it. So literally, you've eliminated 2,000 parts that can wear out. So maintenance-wise, you have no oil changes, you have no fan belt, you have no serpentine belt, you have no timing chain, you have no alternator or starter motor to replace. So a ton of things you're used to maintaining in your car literally don't even exist on the car. So maintenance-wise, I'm expecting to save $5,000 in maintenance over the life of that car. And maybe another $30,000 in fuel. So suddenly, my $70,000 Mercedes equivalent becomes a $35,000 car. A really nice $35,000. That frankly, I think, better than a Mercedes. So we'll stop there.
I'm sure we don't have difficulty believing that Dr. Wielicki had 40 years experience as a climate scientist. I think what he might do in retirement, he might go to work for the Tesla company. In any event, would you join me in one more robust round of applause?